Welcome students to the last probability video. This one finally pulls together statistics and probability by looking at how probability can be determined across two variables. And this is going to be using contingency tables. So launching into it, what is a contingency table? A contingency table provides a way of displaying data that can facilitate calculating probabilities for different events. So what that means is you're going to see a lot of values for different variables, and they're interrelated. So they really depend on each other. So you'll see some intersections in the table. You'll see some totals in the table, and it'll be for two variables, one that's listed in the row and one in the column. So let's look at an example. So in this example, this is stretching before exercise and whether or not it helps to eliminate the possibility of injury. So what we can do is we can survey athletes and we can find out, have they stretched or do they not stretch, and have they had injuries within the past year? So we can make some hypotheses about what we think the relationship is between stretching and injury. And then we can use this data to see if there's any support for that hypothesis. So as you can see, we have injury and stretching. We have injury intersecting with not stretching. We have no injury intersecting with stretching in this number, and then no injury and not stretching is here. Now, when we're calculating probabilities, it really helps to have totals. So let's calculate some totals. And these totals are determined by going across rows to get these totals and down columns. And what's the most important thing to note is that no matter which way you go, this total down here is every participant that are in these four categories. So this total sample is out of 800 people. And why is that important? It's important because if we don't know anything about the athlete of interest, then most likely the probability will be out of the 800. So let's do a quick example. So here we have the probability that an athlete stretches before exercising. And the way we get that is the 350 total of all those who stretch out of the total in the sample. So that is a straightforward probability, just like we've been calculating. And this is where the idea of viewing probability as a relative frequency really comes in handy, because that's what this is. And we can write it as a reduced fraction. We could also write it as a percent. So depending on what kind of format that whoever is requesting this wants the information, or whatever format we want the information in, we can provide that. And remember, all probabilities are between 0 and 1, including 0 or 1 as possibilities. So it should be possible to represent as a percent. It should be possible to represent as a proper fraction. If you don't see that, then there must be an error. Let's do another one. So in this situation, we're looking at the probability that an athlete stretches before exercising. And this is if we know they did not have an injury last year. So this is actually going to narrow down what we're looking at. So remember, I said that 800 is really important, but it becomes less important when we gain some information about the athlete. So in this case, we know that they did not have an injury last year, so we can wipe out injury. We'll just put a big X through that. We don't even need to worry about that column because we know they did not have an injury. Now we can look at the probability that an athlete stretches, and that is going to be only out of the no injury column. And we're going to take the value of stretching out of the total in no injury. Again, when we have more information, that reduces the individuals that we're considering, and that makes the probability out of that group only. So the more information we have, the more we can eliminate people. There's no chance of having someone with an injury because we purposely know that they don't have one. And this is the formal way of representing it. This is the probability that the athlete stretches, and this bar here is usually read as given that they had no injury. So when we're given a piece of information, that removes a big chunk of the contingency table. That's really important to keep track of. So now we're going to do another example. I'm going to give you a moment here to determine what the totals might be. And also to check the total in the entire table and make sure that all of the totals add to that as well. Some of you might already notice that we could probably use Excel to do this a lot quicker. So we're going to get our totals. Again, we can sum across rows, we can sum down columns, and then we could sum all of the inside of the table. The total number of individuals in this case are 205. So what is the probability that a randomly chosen individual from this group is tall? As you can see with that statement, we don't know anything about the individual, so we can't remove any of the table. So our denominator will be the 205. And then we have to figure out where tall is. So tall is right there. The total for tall is 50 out of the 205 individuals. And in order to write that, we'll have the probability of tall being the number that are tall divided by the number of all. So again, you'll have a proper fraction. You can write it as a decimal or you can write it as a percent. These are all possible ways of representing this probability. Now, in this case, we still have a randomly chosen individual, so we haven't removed any of the table, but we're looking for something a little different. In this case, what is the probability that the randomly chosen individual is from a group where they are obese and tall? So, and in this case means both events are happening simultaneously, like we've said in the other videos. And that occurs in this one area where tall and obese intersect. So that value will be 18. That's the value of interest. And since we don't know anything else about the individual, the other value is going to be 205. So let's turn this into a probability. The probability of obese and tall is the number of individuals who are both divided by the number of all the individuals. Again, we have a proper fraction and a decimal that can be written as a percent. Now I'm going through a lot of examples here because contingency tables can be tricky, but incredibly useful and commonly reported. So now let's look at the probability that a randomly chosen individual from the group is tall, given that the individual is obese. So once we're given a piece of information, again, we can wipe out parts of the table. So we're going to get rid of normal and underweight because those are impossible if we've picked someone who is obese. And then that leaves us with just this one row. And within that row, we're looking for an individual who is both. And it'll be out of the total of that group only. Now, suppose we want to flip those. So instead of tall, given that the person is obese, what if we say that we're looking for obese, given that the person is tall? So this is going to wipe out a different portion of the table. The medium and short will go away. We're going to focus on the column tall, and then we're going to look for that same intersection over the total for tall. So this, of course, will change the probability. And again, in order to represent this as a probability, we say the probability of obese, given that the person is tall, is equal to the intersection of the two over only tall individuals. So if you see, what's given is the denominator total. Now, let's look at another example. So now we're looking for a randomly chosen individual from this group who is tall and underweight. Now it doesn't say given. There's no piece of information about the individual that we know. So we're really just looking for the intersection of tall and underweight. That'll give us the value of 12. And because we haven't been given any other information, we're looking at it out of the 205, all the individuals, since we can't narrow it down because we have no given information. Again, in order to calculate this, we're looking at the intersection of tall and underweight. So the number of that over all the individuals, since we haven't narrowed it down. Again, be sure to check that your value is between 0 and 1, just as a fail-safe in case you missed a number, inadvertently put the fraction in the wrong order. You can minimize a lot of your errors just by checking for that one fact. So probability is always between 0 and 1. Will really save you a lot of heartache if you do something incorrect. Okay, we have 2 more examples. So in this example, we're going to try to understand the word or in a contingency table. Now, if you recall, or led us to a general addition rule, right? So we had to look at the probability of one event happening and the probability of another event happening. So those two would get summed together. And then if there was an overlap, we would double count. So we're going to apply that rule to a contingency table, and we're going to look at it in terms of the table itself. So if we're looking at this, here is the general addition rule with all of what I just mentioned. But where are these values coming from and why does this work? So let's look at the 2 categories of interest. We're talking about tall or underweight. So these 2 are the ones that we want. We want to add up all of these individuals and put it over the total, and that's how we're going to get our result. So we can see that 50 and 46, those are our 2 totals for each of the categories. And that's summing the column and summing the row. So the tall is in the column, underweight is in the row. We have 2 totals for both directions. And that gives us these first 2 fractions out of everybody. But this subtracting the 12 occurs because right here, this 12 is in both groups. So we're going to cross it off for one of them. And that's why we subtract, because we've double counted it. So it can't be included in both. And again, we're out of 205 individuals because we don't have any information about the individual themselves. We're just trying to figure out the probability of them being a certain characteristic. So that is or with the overcounting. We mentioned this in the card example. Last but certainly not least, we're going to look at the probability of choosing someone who's not obese. Again, we don't have any information yet about the individual, so we have the 205 total that will remain. And what we're doing is we're getting rid of obese. So let's put a line through that. So there are 2 possibilities for calculating this. We could either add these 2 totals because normal and underweight are both not obese. Therefore, if we add those, we'll get the result we need. Or we could apply the complement rule and instead take 205 and subtract off the 60. Both of these will give the same result. You can go ahead and add the normal and underweight to see what you get, and subtract 60 from 205 to see what you get, and you're going to get the same value. And here it is. The probability of not obese is equal to 1, which is everything, minus the probability of obese. So that would be 205 minus 60, which is 145. And again, like I said, you could add 99 and 46. You'd also get 145. And you can put either one of those over 205. Again, you have a proper fraction that's between 0 and 1. So we know our calculation is good. That's pretty much it for contingency tables. It's a very straightforward method, but incredibly powerful. And I hope it makes sense and it's easy to calculate. And there will also be a very short Excel workbook on this topic and a chance to practice this skill using Excel, which does a lot of the calculation for you. See you in the next video.